The option is there. But here what we do, that for every second we are averaging this part and displaying. So what happens that every 1 second, say when we switch on and starts counting, starts displaying this, then at every 1 second you will see like 77.8. Next 1 second you may see 77. Like that, it goes on fluctuating every second. That means every averaging this part, averaging time, it will be continuously updated. So there will be fluctuating things. After certain time, if you are in overall averaging, that means this plus this, then average, then this plus this, then you go on averaging. Then what happens, after certain time you will be seeing that even if there are some local fluctuations, the overall value will not change. We go on recording this over a period of time, and at the end of the recording period, you will see that the average value LEQ or LAEQ is displayed. It can be recorded, the entire thing can be recorded as a file also. Entire thing can be recorded as a file also for downloading and further analysis. That can be done. Now, as I have told yesterday, that the process is as simple as that. Over a period of time, you are integrating the noise and adding them, then you are taking a time average signal and to find out the LEQ, then expose time. Now, the sound level meters have a very high range nowadays. I think there is someone trying to join. Yeah. Right. So, okay. So now, what we do that, just a minute. We have the previously used to have the analog meters. That means you will never see nowadays unless you have your lab has preserved any specific analog meter. But all the meters nowadays you will see that they are digital meters, all digital meters. So previously you will see some of the photographs are there that I will share with you, where you will see that there is a dial and the fluctuating needle. So continuously fluctuating needle, and then from there you get the RMS values. RMS value. Nowadays the analytical part has become very strong. So what you can do overall, total data you can record and then you can process it out. So we have dynamic ranges as high as 100 dB. That means say minimum it can go up to 100 dB. And there are other machines also where you can see even more than 100. And dynamic ranges means actually if is the minimum trigger level is 40 dB or 30 dB, then you can go up to 130 dB or 140 dB, depending on these things. So there are very high precision machines also where you can go both the side, lower and higher side also. And huge dynamic ranges are available. So inside, since you are, already in second year, so there would be, you understand these things, analog to digital converter, ADC. The ADC will convert the analog signals into digital, and then digital signal processor board that will convert the time varying signal, and and you can opt for the display by using a graphical user interface that you can see through graphical user interface. Now let's very simple, very simple diagram. Let's understand what are the constituents of the sound level meters. What are the schematic? What is the schematic diagram of? Try to understand these things. So this is the microphone that is receiving the signal. That means the sound pressure is actually sensed by the microphone. That means there is a diaphragm or a similar thing on which the sound pressure will act to oscillate this back and forth, and from there you get a signal which is very feeble, very, and we need a preamplifier device to make it stronger for further operations. Then we use the weighting network here. So what is this weighting network? After preamplifier, what does it do?
Resonates particular frequencies.
Try once again, try.
Or maybe it like adds the A weighted.
A weighting network. So if I select a weighting network, then what will it do? If I select a weighting network, then what will be the function of the a weighting network? For processing the signal that is coming through preamplifier and going further towards the end for recording. What did you do in that? The problem that I have shown, a list of values.
So
Then
it
there's some, yeah.
like it corrects each value and then like adds it to get an equivalent value.
Okay. So what it does it do? Same thing. What you do, the same thing has to be done by the electronic circuitry, because the concept is yours. The concept is that there will be a whole spectrum of signals, and which is already pre-amplified because it's very weak. So we get an amplified signal, and then we go for, say, it depends on a weighting correction, or x may be a, c, or z. So you choose A, so it goes for A weighting corrections. That means the signals which were coming flatly, this is a flat response microphone within the 20 hertz to 20 kilohertz. This is a flat response microphone. It does not differentiate between frequencies. So that you have to design also. And you must know also that what is the behavior of the microphone. What is the sensitivity of the microphone across the frequencies. That is another part of the digital electronics. Because if you have to make it flat, then you have to know what kind of microphone sensitivity is there. That we are not including here because we are not learning digital electronics here. The idea is that we are telling something and you are asking the circuit to do it. How do you do that? Because see, when you are telling that this microphone is a flat response microphone, then you have to ensure that it is equally responsive to all the frequencies. So you need to send different signals of different frequencies and see the output in the oscilloscope. And from there you have to find out what is the frequency response curve of the microphone. That means from say 20 hertz to 20 kilohertz. And when you are giving say 10 dB or 30 dB or 40 dB amplitude, then whether it is flat or whether it is like this, what kind of curve it is. So according to the behavior of the microphone, characteristics of the microphone, you need to add, design the preamplifier so that it corrects that thing and make it absolutely flat, complete flat. The amplifier will also cause certain additional noise, so it has to be a very high quality preamplifier so that it does not add any additional noise into these signals that we have already received. In the weighting network, what it will do, that it will receive a band of frequencies or the sound waves of different frequencies. Yeah. So they say our preamplifier gives us sends a signal of this thing, because across all the frequencies, before you go for weighting network, you need a frequency analyzer also. That means the circuit also divides, the digital circuitry also divides the entire spectrum into the center bands of the octave frequency. Or in case of one third octave band, it will be further divided into smaller segments like this. So there will be a huge number of huge data in the input side. And there you must know what is the correction for. So this is the linear level. So that means we are getting the linear level data from the preamplifier. Now we go for a weighting correction here. This is the a weighting correction through the your weighting network or filter. So there, when you are passing through, the filter, then this will change to this, the last line. It will come to this. So that is the function of the weighting network. So if I use a Z network, then what will happen, that whatever you are giving in the linear level will be directly passed. This is basically bypassing the network. It is basically bypassing the network, basically. And what we do actually, we try to make a band pass filter. I have said that from 20 hertz to 20 kilohertz is our range of interest. Outside that, ultrasound or infrasound, we are not interested. So at best, these filters, which are not filters, they will only filter out the top portion and bottom portion beyond the sonic range. So the infrasonic part and the ultrasonic part will be completely eliminated. Completely eliminated. The rest of the things eliminated means heavily attenuated. That will not create any difference there, any difference in the final output. So in the A-weighting correction, we will get the linear level of sounds converted into A-weighted level series of sound. So this frequencies will be used for the purpose of the next level of operation. What is that? So that part, let me see here. So from the weighting network, now it is filtered. After that, after that, for further processing, because it goes through a number of circuits now, so we need further amplification here. Further amplification here. So it goes to another amplifier. Because now we'll go for, you can record it from here, output jack. Record it. Previously we used to even record this into tapes before the digital circuits came. So we used to record in tape because it used to be huge, signals. So if you cannot record it in this thing, um, your in any say IC or similar kind of thing. So what we had the option of recording these things in spool tapes. So it will go from one to other. You might have seen in films also nowadays, or you search spool tape recorders, where you can see it is more or less, looks like a bigger cassette recorders, where you can record this here, and then again you can later on you can play and play and then use those signals for further processing. Now once that is done, then we are going for rectifier. So can you tell me what this rectifier is doing here? analog meters. In digital, the process is a little different, but in analog meter, what is this rectifier is doing here? Have you heard about rectifier before? Do you have electrical technology in first year or second year?
Yes, yes, heard.
You heard about rectifier. What is rectifier?
Sir, it converts DC into AC, sir.
DC into?
Sorry,
It's
sorry,
the
AC
opposite.
into DC, sir.
उल्टा कर दिया था, डर गया था मैं थोड़ा सा. So AC into DC, AC into DC, isn't it?
Yes, yes.
Yeah. So what does it actually? How we say assemble rectifiers? Have you seen any rectifier ever? Simple rectifiers, small diodes. So I have all those things with me, but it's difficult to show those things. But for our, making something enjoyable, let's see how does it look like. Rectifier diodes. These are basically solid state diodes. My computer is slow today, I don't know why. Yeah. So these are very well known diodes. Yeah, this one. So this side, this side is the anode, anode, and this side is the cathode. The silver part is the cathode. That means the current can flow in one direction from your anode to cathode, right? So what we do that in AC signals, and these are different. This you will see if you open an electronic circuit, you will see. So what you see there here, especially this one, is the symbol of the rectifier. Symbol of the rectifier. But this is not the rectifier circuit. This is the rectifier, the device itself. This is having the the major function in the rectification of the signal. So it is now I think you remember this thing, the anode and cathode and this part. So what we do actually, we pass the signal through through the rectifier, and just a minute. So we have a time varying signal which is having so many components, right? So many components. I mean, not one. There would be many. There will be many time varying signals. So this will be passed through the rectifiers, and it will give a equivalent value here, rectified value. That means when we in AC circuit also what we do, that we have say plain sine wave, absolutely simple and harmless AC signal. Fine. So now where here what happens, that when you are rectifying, then you are making it a DC. Making it a DC. So when we talk about the 220 volt line or 230 volt AC in our household use, then what voltage is this? Is it AC or is it DC? Can you tell me? AC is an alternating current. So how can it have a fixed value? We call at our home, what is the supply? We say 230 volt AC. 230 volt AC. How is it possible?
But it's the RMS value.
It is the RMS value. That means if we rectify, that means if you are when you are measuring with the meter, then it will show you the RMS value. But if you want to see the nature of the signal, then you have to use an oscilloscope and see how it is varying over a period of time. So rectifier will ultimately give you the equivalent value. Now question is that, remember these things which are not written here, that whenever when you are using an analog signal, then you have to make the scale in such a way that whatever amplification you have done in between has to be compensated in the dial. That means, say if you are doubling anything or making it 10 times, but your the signal it remains 100 dB, 100 dB. So whether you are amplifying it or something, or the equivalent, whatever transformation you are doing, ultimately you have to show that it is hitting the 100 dB. So how do you do that? You have to make some standard, standard calibrators by which you can calibrate it. So in analog also you can calibrate, in digital also you can calibrate. So once it is rectified, this now the in digital meter you can see this kind of display direct. Even the variation over a period of time is now plotted. So you can see it how it is changing over a period of time. That you can directly see. Also you can switch over to certain octave bands. That means you can ask the meter to show in 1 by 1 or say 1 by 3 octave bands. So next week I'll be connecting another computer from the laboratory where the demonstration will be given by the research scholars how it is used, and in field condition also how it is used, what are the different components, and also there are certain interesting thing about the sound level meters. Very simple but very interesting things about the small meters that we'll be discussing that day. So here, apart from the display, we can go for recording also. I mean, there is direct recording also after display, and before rectification also you can record the AC signals for further processing. That means whatever manipulation you have to do, you can do it from the or whatever processing. We call it now post processing nowadays. We call it post processing of the signal. Post processing. That means it is not done at the time of recording. It is done at the laboratory, in the laboratory. So when you are downloading the signal and then you are replaying. That means in spool tapes also you are recording and then playing it, and then you are getting the signals into another computer or any other instruments and analyzing it. So these things are done by post processing, at the stage of post processing. Now what are the things that apart from the LAQ we want to know? We need to know the LEQ, that means which is not weighted. We must know LAEQ, which is a weighted L equivalent. And also there are quantities which are very interesting, like L10. That means sound pressure level exceeded 10% of the time. 10% of the time it exceeded that level. There are certain guidelines where the impulsive forces are not to exceed 10% of the time. So you must know L10. That means it is nothing but the same data used for different purposes for your understanding of the nature of the variation. Also L90, the sound pressure level exceeded 90% of the time. That means there are some minimum criteria and 90% of the time it exceeded. So from there you can understand the nature of the sound. And we have the internal filter networks, which I have extensively discussed. Internal filter networks, where you have the choice of A and C. Z is basically a band pass filter, does not do any filtering at all. And that is called the all pass linear. The all pass linear arrangement without any weighting. So you can simply bypass it also. This is very important to understand. All pass. It is not doing anything. When you are selecting A, it will be correcting the signal as per A weighting, your octave band corrections, and then your C weighting will be doing mostly correcting below 63 Hertz and above probably 4 kilohertz or 8 kilohertz. Yesterday we have seen it. So these things will be done by weighting filters. This I have shown that what is the difference between LEQ and LAEQ. Now for uh, when you are measuring very high level of these things, when very high sound levels are to be measured, such as above 140 dB, a low sensitivity microphone should be chosen, because if you are making it highly sensitive, then the microphone even can get damaged. Not only that, you are not required to give any low resolution. That means 1, 2 dB or 5 dB variations is not required, because you are measuring everything above 140 dB. So even 5% variation will be very high. So you do not require a microphone which is very highly sensitive. So you need a low sensitivity. But when you are measuring at very low level, like 30 dB or below, then you should use the highly sensitive microphone. In industry, in say where you are using measuring in the plants, where the sound noise is say around 90 to 100 dB or 105 dB, you can use a class 2 microphone that I'll be showing in next slide. But where you are in a lab environment, or where these classes are going on, some demonstrations are going on, many other things where you are analyzing the sound of birds or any other animals and other things. So where the overall sound is very low, you need to detect very low sound. So there you can use a high sensitive microphone, so that the little variation also is recorded by the microphone. Otherwise, in industrial noise, what we can do, we can use a class 2 microphone for all purposes. Now, as I have told that, that we have a very dynamic range, 100 dB to 120 dB also nowadays. And we have, two response times. This is very important, the response time. That means one is level fast. You will see that in the sound level meter we have fast option and that is slow option. In fast option, it has a time constant of 125 millisecond and is designed to approximate the response of the ear. That means a time variation of 125 millisecond gap can be detected by ear. Otherwise, in between, if there is a change, it cannot be differentiated. The other level is slow. This has a time constant of 1 second. And this is not simulating the response of the ear. It is useful in older sound level meters for determining the average levels. Average levels. So nowadays also for long-term averaging, we have a slow time constant, and for showing the first response, which is mimicking the human response, then you can use the fast response. There will be variation in the readings. There will be little variation in the reading, but when you are taking a long-term measurements, the values should not be very much different. The sensitivities, and classes of sound level meters are included in the IEC 61672 Part 1 2013. Now it is updated also, that's why it is up to 2013. So what is IEC? Can you find out through Google? IEC, or if you know, you can tell me. IEC 61672 Part 1 2013. Just type it in the Google and then search in the Google and tell the entire title of the standard. This is an international standard. So you try to find out the entire title. When you are, uh, in charge of this kind of thing, you know things theoretically, practically, and legally also. What legal bindings are there when you are trying to something which is related to environmental noise and human health. Yeah, can somebody tell me what is the full title of IEC 61672 Part 1 2013?
It is something like international standard. Some PDF is there, first edition.
First edition. So what is the title of this IEC 61672? There should be a proper
Sir,
title for, yeah.
International Electrochemical Commission.
That is fine. International Electrical Commission. What is this 617 to 672 is doing?
So it's electroacoustic sound level meter.
Electroacoustics?
Sound level meters. The
Sound level meters.
yeah.
That means this commission is giving you directives based on scientific data as to what should be the technical specifications of sound level meters. This standard, I don't have a clock here. So what's the time? Do I have time? What's the time now? 8:30, no?
845.
8:45. Okay. Okay. So the standard prescribes the technical standards or technical specifications of the sound level meters that you are making, you are selling, you are using. Commonly we have two classes, class 1 and class 2. Class one is, by name, the precision is very high, precision sound level meters. So even though it is not very helpful, so, in legal cases, it had been cited that why you have not used class 1, you should use class 1. Even though in environmental noise, 1 or 2 dB difference does not mean anything. Unless somebody is challenging it is, 101.2 dB, it is not 100 dB, then you cannot go for, and why should I go for precision, such a precision, unless it's a lab work. So the class 1 meters are intended for laboratory use or field use where accurate measurements are very much required. You are using some barriers. So if you are using some noise barriers and you are sending signals and then you are receiving here and you are changing the barrier, maybe you are doubling the thickness of the barrier. So you need to very clearly know what is the attenuation through the barrier, what is the sound decrease in sound level when it is passing through that barrier. There you require the class 1 sound level meter. Otherwise, you can use the class 2 general purpose sound level meter intended for general field use and for recording noise level data for later frequency analysis. So class 2 is very common, but of course, I personally, I used both of them. I used class 1 and class 2 both. Okay, just a minute, I'll come back. ₹10 वाला Okay. Now, in the next class, we'll be doing some, numericals for the sensitivity of the microphones, how to define, and then how to select a microphone with a particular sensitivity. Now here you see the microphone sensitivity. So how do you know? Not only that, how to calibrate the instrument, because when your machine is showing 93 dB or 93.7 dB, then how correct, how much, what is the what is the confidence that it is a correct level of correct display. Or so that error, the internal circuitry error has to be compensated by calibration. But there are other issue for calibration also when you are using certain machines like the microphones, which are basically getting the mechanical energy continuously for years together, and also when the temperature varies. So from very low level, maybe from the minus 2 degree or minus 7 degree to as high as 40 degree or 50 degree, then the physical characteristics of the microphone, the sensitivity also changes. So when you are going outside, especially in field conditions, so and when there is a temperature difference, and also due to aging process, that means you have used this for 5 years or so, so there will be expected, you can expect that there will be certain change in the characteristics of the microphones. So for that we need some kind of we apply some tonal acoustic signal, the tonal acoustic signal of known sound pressure level. That means we know that this is 100 dB or it is 94 dB. We know it. Then we put very close to the microphone, or we insert the microphone capsule into the calibrator body. The microphone is inside, so it receives no other sound. So the generated sound directly goes here, and you see the display. Okay, so now we have to use the preset gain control, and if the preset gain controls are not available, preset gain control is basically like adjusting the volume control of something, in in the, so you have to adjust this potentiometer in analog circuits. That means you will have a knob kind of thing, you rotate and adjust it, preset. But in digital circuits, you have to input that data, or you simply press a button called calibrate. What it will do, whatever you are saying, you actually, the digital machines are dumb in that way. So it is already programmed, so you don't have to understand anything. You press calibrate, it is calibrating. That means what it is doing, that instead of showing say a preset, a particular value, if it is not showing that, it will automatically adjust. That means if your calibration is 94 dB, 94 dB at a particular frequency, and if it is actually 96, then it will automatically adjust to 94. Or if it is 92 dB or 93 dB, it will automatically adjust to 94 dB. So the pressing just by the button is enough. Sometimes you have to give an input also. So those are over. Now it is a press button press, and then it gets automatically corrected. Most of the devices nowadays use the 1 kilohertz signal calibration frequency. Most of the signals, most of the devices, the sound level meter devices, use 1 kilohertz as a calibration frequency. 1 kilohertz as a calibration frequency. Why we use the 1 kilohertz as a calibration frequency? That's the question. The question ऐसा है कि we are using a peculiar frequency. If you remember A, C, or Z, you will see, because the maximum correction is given in A weighting. So if you see in A weighting, what is the correction in 1 kilohertz? Dibasri, what is the correction in A weighting for 1 kilohertz?
I'll have to see.
You have to see.
I
That means
don't,
you forgot already.
I don't remember it.
So many classes every day, no? So you forget all these things. So can you see it? Do you have any record?
Yes, sir, I'll see it.
Found it? Anyone else? What is the awaiting correction for 1 kilohertz signals?
So is it 0?
Who's speaking?
Hemant.
Hemant, it is absolutely correct. For 1 kilohertz, the correction is 0. That means whether you switch on the awaiting network or switch off the awaiting network or you switch off all other networks, the value will be same. Value will be same. So that means without any interference, whether you are using A, C, Z or switched in or out anything, the value will remain same. That's why there will be no chance of making any mistake. That's why the manufacturers are instructing us that you should use the 1 kilohertz calibrator so that there cannot be any. So there are many people who doesn't know so much like you know. So they'll be using. So you'll be sending most of the time some technicians to assist you because it's not a lab work. So you can train some people. They will go to the field, get the data, come back and inform and report to you, sir. This is the result that you got. So you don't really know what that guy has done, during measurement. So what calibration, calibrators, I will show you the calibrators also in the next class. We have the calibrators. So when you are going for field work, then you must carry the calibrators in that particular condition, especially when the temperatures are low or very high, in summers or the winters, then there would be certain changes. And you must, and definitely when you are using some array of microphones, like say a number of sound level meters, 10 sound level meters all over, you are doing a large scale survey. Then to compare the values that you are getting through all those 10 sound level meters, you must ensure that the sound level meters are equally sensitive. That means if it is brought near the same sound, same source of sound, source of noise, then it should show the the record the sound or display the result equally. That means their values should be same all over. So the calibrators use 1 kilohertz as the calibration frequency, right? So the calibration is done using 1 kilohertz frequency. Whether now you switch on a awaiting network or you switch off the awaiting network, doesn't matter. That's why it is said calibrators operating at other frequencies require all waiting networks to be switched out. That means if you are not using 1 kilohertz, then you must ensure that all the waiting networks are switched out. All waiting networks are switched out. Otherwise, it will modify, it will correct, it will make changes which you do not want. So that's why, if the question is that why you use 1 kilohertz, then the answer is that whether the waiting network or any other waiting network is switched in or out, the results will be same. That is why we use these things. In the next class, I will start with the calibration, and then we'll quickly try to see the sound level meters, the measurement process, and all those things before we switch over to environmental noise chapter and some industrial noise control. How you do that? That part will be starting in the next week. I'll be sharing this, I think I'm sharing all these PPTs. Thank you very much. See you in the next.
Thank you.
Thank you. Thank you.
Thank you.
Thank you, sir.
Thank you.